Welcome to this presentation on the log likelihood object in Eviews. This powerful tool is designed for maximum likelihood estimation and custom optimization, allowing you to go beyond standard Eviews menus. The LogL object provides a general, open-ended tool for estimating a broad class of specifications by maximizing a user-defined likelihood function. We'll explore how to harness this flexibility to tackle complex econometric models that traditional estimators can't handle. Standard estimators like OLS, ordinary least squares, or standard ARIMA, Autoregressive Integrated Moving Average models, operate under a fixed set of assumptions. The LogL object provides total flexibility, acting as a key to unlock estimation for complex research needs that don't fit standard tools. You should use the LogL object whenever your model's specification doesn't match a predefined command in Eviews. The process begins with theory, where you define the probability density function, or PDF, of your model. Next is setup, where you create the LogL object in Eviews and define the parameters to be estimated. Then comes specification, which involves writing the Eviews code that defines the log likelihood contribution for a single observation. Estimation is the step where Eviews optimization algorithms work to maximize the total likelihood function. Finally, diagnostics are crucial. You must check the gradients to ensure the algorithm successfully found a true maximum. The decision map on the right helps guide your choice. If your model is linear, use OLS. If it has standard volatility clustering, use ARCH. But if it's a custom specification, the path leads directly to using the LogL object. The core of maximum likelihood estimation is the log likelihood function, denoted as L of theta. It is the sum of the individual log likelihood contributions, log LT of theta, for each observation from t equals 1 to t. The vector theta contains all the coefficients you want to estimate, for example, C1 and C2. Your main task is to specify the formula for a single observation's contribution, LT. Eviews automatically handles the summation over the entire sample. The @LogL keyword is essential. It tells Eviews which series you have created to hold the value of log LT of theta for each observation. For example, if you are estimating a simple linear regression with normal errors, your code would define a series, say myLogL, that calculates the value of the normal PDF for the residual of each observation. You would then write @LogL myLogL to tell Eviews to sum up this series. This powerful method, however, rests on several critical assumptions. Let's review them to ensure our estimation is valid. First, we generally assume observations are IID. However, this can be relaxed to allow for time dependence, as seen in GARCH or AR models. Second, correct specification is vital. The functional form of the PDF you assume must be the true one, or your estimates will be biased. Third, the model must have identification. This means each distinct set of parameter values must produce a different likelihood value. You can't have multiple parameter combinations leading to the same result. Fourth, the likelihood function must meet regularity conditions, meaning it must be continuous and differentiable so that optimization algorithms can find the maximum. A critical warning: non-identified models will result in singular covariance errors or failure to converge. Always ensure your math is solid before you start coding to prevent these issues. The objective is different. OLS aims to minimize the sum of squared residuals, whereas MLE aims to maximize the likelihood function. The solution method also differs. OLS has an exact, analytical solution found through matrix algebra. MLE, on the other hand, requires an iterative, numerical search to find the solution. Finally, assumptions about variance are distinct. OLS assumes constant, homoscedastic variance. With the LogLog object, the variance structure is flexible and can be defined by the user. Eviews LogLog uses iterative hill climbing algorithms like Newton-Raphson and Marquardt to find the peak of the probability density function. The graph illustrates this MLE search process, showing how the algorithm takes iterative steps uphill on the likelihood function, like a mountain climber seeking the highest peak, until it reaches a point of convergence, which should be the maximum. To begin, you create a new LogL object directly from the Eviews main menu. Navigate to Object, and then select New Object. In the New Object dialog box that appears, scroll down and choose LogL from the list of object types. A useful tip is to name your object immediately. For example, in the command line, you could type LogL myModel. If you create an object through the GUI and close its window without saving, all your work will be lost. Naming it saves it within the work file. The first step is parameter initialization. Here, you declare the coefficients you want to estimate, like C sub 1 and C sub 2. You can use the @param keyword to set initial starting values. Next, you can create intermediate series. These are temporary variables, like the residual res, that help simplify the final likelihood calculation. The third step is the objective declaration. This is where you use the @LogL keyword to tell Eviews which series holds the final likelihood value for each observation. Finally, you perform the likelihood calculation. This is the line where you write the actual mathematical formula for the log likelihood of a single observation. In the code shown, param C sub 1 0, C sub 2 1 initializes C sub 1 to 0 and C sub 2 to 1. The residual res is calculated. Then, @LogL 1 declares that the series LogL 1 will contain the objective function, which is calculated on the final line. After writing the specification, the next step is estimation. Eviews provides several options to control the optimization process. This slide shows the LogL estimation options dialog box in Eviews. Here, you can select different optimization algorithms. Marquardt is the robust default algorithm. BHHH, or Bernd-Hall-Hall-Hausman, uses the outer product of gradients and is useful for larger models. You can also adjust the max iterations, which is set to 500 here, and the convergence tolerance, set to 0.0001. A best practice is that if your model doesn't converge, try switching algorithms, for instance from Marquardt to BHHH, or increase the maximum number of iterations. In this case study, we will estimate a regression model where we suspect heteroscedasticity. The mean equation is a simple linear model. Yt is a function of an intercept c1, a slope c2 on xt, and an error term epsilon t. The key innovation is the variance equation. We hypothesize that the variance of the error term, sigma t squared, is not constant. Instead, it depends on another variable, zt, according to the formula sigma t squared equals c3 zt to the c4. Our goal is to estimate the four parameters, c1, c2, c3, and c4, using the LogL object. We suspect the variance of y is not constant, but depends on variable z, as shown in the data work file. We must translate this mathematical hypothesis into Eviews series for estimation. First, we declare the objective series using @LogLog1. This tells Eviews that the series log1 will contain the log likelihood contribution for each observation. Next, we code the mean equation. We create an intermediate series called res to hold the residuals from our regression. Res equals y minus c1 minus c2 times x. Then we code the variance equation. We create another intermediate series called var to store the changing variance, which is defined as var equals c3 times z to the c4. Finally, we write the log likelihood for a normal distribution. The formula is log1 equals log of @dnorm res divided by @square root var minus 0.5 times log var. Let's break this down. @dnorm of x is Eviews' standard normal density function. So, log of @dnorm res divided by @square root var calculates the log of the standard normal density for our standardized residuals.
The second term, minus 0.5 times log var, is the Jacobian adjustment, which is essential when the transformation from the error term to the standardized residual involves a varying variance. Remember that at log must always be assigned the final value for the observation's log likelihood. Without initialization, Eviews assumes all parameters start at 0. In our model, if the starting value for C3 is 0, the variance, var, will be 0, causing a critical error as you cannot take the log of 0 or divide by 0. By using the @param statement, we provide safe starting values, like C3 equals 1, that allow the optimization algorithm to begin its hill climbing search from a valid point. As a pro tip, always initialize variance parameters to positive numbers to avoid these domain errors from the start. This ensures the estimation can proceed smoothly. After estimation, Eviews provides a standard output table with coefficients, standard errors, z-statistics, and p-values. To test our hypothesis of heteroscedasticity, we focus on the parameters of the variance equation, specifically C4, the var power. We check the probability value, prob, for C4. If this value is small, typically less than 0.05, we reject the null hypothesis that C4 equals 0. A significant C4 confirms that variable z does indeed affect the variance, meaning heteroscedasticity is present. In the results shown, the p-value for C4 is 0.0001, which is highly significant. This provides strong evidence to conclude that heteroscedasticity exists and our model is well specified. The table also reports the final log likelihood value, which is useful for model comparison using likelihood ratio, or LR, tests. The final step in our workflow is to check the gradients of the likelihood function at the solution. The gradient measures the slope of the likelihood function. At a true maximum, the peak of the hill, the slope should be 0. Therefore, we check if the gradients for all our estimated parameters are very close to 0. If the gradients are non-zero, it suggests a problem. Either the algorithm stopped prematurely before reaching the peak, or the likelihood function is not smooth, violating the regularity assumption. The output shows the gradients for C1 through C4 are all extremely small numbers, on the order of 10 to the power of -6 or 10 to the power of -7. This is effectively 0, confirming that the algorithm successfully found a peak and the optimization was successful. If you encounter missing values in @log, it often means there's a domain error in your likelihood function, such as trying to take the log of a negative number or dividing by 0. The primary solution is to carefully review and adjust your starting values for the parameters. A singular covariance error indicates that your model is not identified. This means there isn't a unique set of parameter values that maximizes the likelihood, and you'll need to simplify your model specification. When you see convergence not achieved, it means the optimization algorithm couldn't find a maximum within the specified limits. To address this, try increasing the maximum number of iterations or switching to a different optimization algorithm in the estimation options. A valuable debugging tip is to use the show LogL series command for the series you've declared with @log. This will open the series in a spreadsheet view, allowing you to inspect it for NA values, which pinpoint exactly where the log likelihood calculation failed in your data, helping you to diagnose the error more precisely. The LogL object doesn't have a built-in way to enforce constraints, such as ensuring a variance parameter is always positive. To handle a positivity constraint for parameters like variance, we reparameterize. Instead of estimating C directly, we estimate C1 and define var equals @expo C1. Since the exponential function is always positive, this enforces the constraint. Similarly, to constrain a parameter to be between 0 and 1, like a probability, we use the logit transformation, prob equals @logit C1. For missing data, manual listwise deletion is required. An advanced tip: transforming parameters ensures stability but changes the interpretation of the coefficient. You may need the delta method to recover standard errors for the original parameter. This slide provides a handy syntax cheat sheet for key Eviews commands and math helper functions, along with essential references. Under object commands, we have @LogL name to define your objective function, @param_c_val to set initial starting values for coefficients, and @temp_list for cleaning up temporary series. For math helpers, @dnormx gives you the probability density function for the normal distribution, @cnormx is the cumulative distribution function for the normal, @coefcov provides the covariance matrix, and